So my talk will contain two main parts. First, I will explain the main statements. There are four main statements. And then I will say a few words about proofs. And there is a third part of my work about complexity, but complexity will be not really involved in this talk. So basically, and I have to say that there is a preprint now on arXiv, which is called Which Nilpotent Groups Are Self-Similar. So the goal of the talk is to explain some connection between the symbolic dynamics of nilpotent groups and the geometry of the Nil manifold. So let's start. So first I need to define what self-similar means. I start with a finite alphabet A, so a finite set. And I denote by A omega. It is a set of infinite words over A. So there are words of the type A1, A2, A3, and so on. So sometimes they are called, I think, semi-infinite because they have a first letter, but then it is like this. And of course, there are letters over A. And now assume that gamma, group gamma, is acting on the set A omega. And we say that the action is self-similar if it satisfies the following condition. So it means that whenever you choose some element gamma in gamma and some letter A in A, then there is another letter B and another element gamma A in gamma, such that gamma of AW equal B gamma A of W for all W in A omega. So what means this notation, AW? It means that it is an infinite word starting with A, and what's next is the word W. This is the definition of self-similar group. And the group gamma is called self-similar if it admits a faithful self-similar action on some A omega for some finite alphabet A. So this notion has been introduced in the 80s in two places, first in the work of Grigorchuk and also in joint work by Gupta and Sidki. And I have to say that, yes. And the generic question, of course, is which groups are self-similar? But this is a generic question which cannot be without answer, of course. But now we can consider finitely generated torsion-free nilpotent group. Later on, it will be called FGTF for finitely generated torsion-free. And this question has been raised in some talks by Said Sidki. Probably, I didn't see this in print, but it has been raised many times in talks by Said Sidki. And exactly, Said Sidki was interested in some technical notion which is called transitive self-similar actions. We'll explain later on what it is, because probably if we are just looking at self-similarity without anything more, this question is not so interesting. Say, really, it starts to be interesting when it is transitive. So now, to explain what we will do, we need much more definitions. So unfortunately, I will start with definitions. So I will start with the notion of transitive minimal or free self-similar action. And I will explain also what is the notion of spatial and very special gradings of Lie algebras. So really, we'll explain these definitions, and then our main theorem connect actions with spatial or very special gradings of Lie algebras. That's so, but first, of course, we need to define what they are. So first, start with the notion of minimal actions. So now when you start with A omega, sometimes this set is called the boundary of the 3A star. It is, of course, a projective limit of A to the n. And it is endowed with a natural topology, which is the profinite topology. But equivalently, if you don't like profinite topology, I know that some of you like profinite topology, but anyhow, there is an equivalent definition, is that if you take two infinite words, say distinct words, say you say that the distance of W and W prime is 2 to the minus n if the first n letters are identical. Exactly, the first n letters are identical. And this D is a distance, ultrametric distance, and so it defines a topology, and this is exactly the topology on A omega. And now the action of gamma on A omega is called minimal. It simply means that all gamma orbits are dense. Because here we are in the ultrametric world, indeed, really it's enough that one orbit is dense. If one orbit is dense, then all orbits are dense because gamma acts by isometry here. And now there is a notion of transitive action. So transitive action is not transitive. This is the first important thing to say. It's a very weak notion. So recall the definition of what a self-similar action is. So self-similar action means for all gamma in gamma, for all A in A, for there is some B in A, such that blah, 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 blah. So just let's start with the beginning of the definition. And the beginning of the definition is enough to define the action of gamma on A. And the action of gamma on A is simply, it's an A to B. So you don't have to check what's next in the condition. And a self-similar action of gamma on A omega is called transitive if gamma acts transitively on A. So this is a very weak notion of minimality, very technical notion, but which plays an important role in what follows. Let me explain the difference between minimal and transitive. What minimal means? It means that each orbit is dense, so it means that for all words, W and W prime, then their distance is less than epsilon for any epsilon if you let gamma act. So it means W prime is at distance less than epsilon of the orbit of W. This is what minimal means. And now transitive, it is exactly the same, but simply for epsilon equal 1/2. So it means that for all W prime in A omega, there exists a gamma such that the distance of gamma W of W prime is less than 1/2. It means that two orbits, the distance between two orbits is less than 1/2. So this is what transitivity means. So it's much weaker than So transitive means a very, very weakly notion of transitivity. And let's say that the group is minimally self-similar. So we already know that what a self-similar group, and we say that gamma is minimally self-similar if gamma admits a faithful minimal self-similar action on A omega for some finite A. And similarly, here we define what minimally self-similar is. We can define what transitive self-similar is. So the group gamma is called transitively self-similar if and only if gamma admits a faithful transitive self-similar action. Okay, so there are two notions. I don't know the terminology. Should I call it minimal self-similar or minimally self-similar? This is a bit unclear to me. But there is also a notion of for free. And I don't want to say that gamma is free self-similar because a free group is something which is already defined. So that's why I use minimally and transitively here. So similarly, I say that gamma is freely self-similar if it admits a free self-similar action on A omega for some A. Free action means that it acts freely on A omega. Okay. And now I can combine free and minimal. So I say that the group is freely minimally self-similar if it admits a free minimal self-similar action. So now we have the main definition. And what I'm mostly interested is minimal actions and free actions, which are something which is very clear. So now that we define what self-similar actions are, I need to define what the spatial gradings are. So I start with the Lie algebra M. And let's recall what a grading is. It's simply a decomposition of M into pieces indexed by K in Z, by integer. And what we want that the bracket of an homogeneous element of degree K and an homogeneous element of degree L is homogeneous of degree K plus L. That's the definition of a grading. And now I came to the main definition, what a spatial grading is. So a grading is spatial if, okay, let's consider the center Z of M, and you want that the zero component of Z is zero. It should be, I should have said that when you have a grading of the Lie algebra, it provides you automatically a grading of the center. Okay, so this is spatial. It means that the zero component of Z is zero. And a grading is called very spatial if indeed the zero component is zero. So of course, very spatial implies spatial. Now that I have a group, gamma, a finitely generated torsion-free nilpotent group, I want to associate to this group a Lie algebra. And this is done using, it's well known how to do that. It is due to Malchev. I think it is due to some paper of Malchev in the 50s. So it's not really new mathematics, but I will recall what Malchev completion is. It's important to recall what Malchev completion is because different authors use different terminology for that, because Malchev papers contains I forgot 5 or 6 theorems, and depending on the authors, they refer to Theorem One or Theorem Two. So completion is not so clear. But anyhow, using Malchev, one of Malchev theorems that there is a unique connected and simply connected, so CSC, it's connected and simply connected, nilpotent Lie group N, such that gamma is a co-compact lattice in N, a discrete subgroup, such that the quotient is compact. And now we can define a Lie algebra, NR, which is simply the Lie algebra of this group, the Lie algebra of N. And what NC is simply the complexify of this Lie algebra. Now, everything has been defined, and now I can state the main two theorems. And the main two theorems are conditions for existence or minimal self-similar actions or free self-similar actions. So Theorem One is about self-similar actions, minimal self-similar action. So the following three conditions are equivalent. First, that gamma is transitively self-similar. So this is a kind of very technical condition. The second condition is that gamma is minimally self-similar, which is means an action, self-similar action with dense orbits. And third, the Lie algebra NC admits a spatial grading. So you see, this is it gives a very explicit condition. But we have to be careful about the equivalence of 1 and 2. I don't mean, by this, I don't mean that transitive actions are automatically minimal. It's totally wrong. I mean that if there is a transitive action, then there is another action which is minimal. And usually there is absolutely no connection between both alphabets. Okay. And existence of the spatial grading is something very clear. And indeed, in Theorem One, I can say that this is equivalent to something, to another conditions, but really I do prefer to state it condition 3, and you will see just at the end why I want to state it like this. Now, Theorem 2 is really similar, but for free actions. So Theorem 2 is that it is equivalent, the following conditions are equivalent, that gamma is freely self-similar, gamma is freely and minimally self-similar, and NC admits a very special grading. Of course, as before, I don't mean that free self-similar action is automatically minimal. That's totally wrong. And again, if you have a free self-similar action, then there exists a minimal, there is an action which is both free and minimal, but again, there is no connection between the alphabet for A and the alphabet for 1 and the alphabet for 2. As you will see, it involves some difficult procedure to go from 1 to 2. And also, I would like to make a remark that in both theorems, the grading are not always defined over R, and it's really necessary to go to the complex, to the complexify of the Lie algebra. I have example for which the real Lie algebra has no grading at all. So not only non-spatial grading, but no grading at all. So really we need to go to NC. So that's a very important condition. Now, I would like to explain some corollaries for the theory of Nil manifolds. You see, these are statements for self-similar actions, Theorem One and Theorem Two. But now I would like to connect this to the geometry, the differential geometry of Nil manifolds. So let me remember what a Nil manifold is. First, a Nil manifold simply means a manifold M of the form n modulo gamma, where n is a connected and simply connected nilpotent Lie group, and gamma is a co-compact lattice. So obviously, gamma is the fundamental group of M. So later on, when I will speak about a Nil manifold, I will express the statement in terms of its fundamental group. But if you write it as n modulo gamma, then really it is the gamma here. And of course, of course it is gamma is a nilpotent group, so it's. So let's first explain. So there are two corollaries. One involved the Anosov geometry, and the second one involves affine Nil manifold. So I would like to explain first what the Anosov diffeomorphism is. So let's take any compact manifold. It could be Nil manifold or not, does not matter. And you take a C1, a diffeomorphism which is C1. If you prefer, you can choose it smooth. I don't know exactly. Yeah, now I know. I know that there is a lot of difference between C1 and smooth. Here we will see no difference, but I don't know exactly why, but in differential geometry, they really enjoy this hypothesis C1, but don't ask me why. And diffeomorphism is called Anosov if you can split the tangent bundle into EU plus ES, where each piece is invariant by the differential of phi. So it's a continuous splitting usually. And we want that the differential of phi restricted to the stable bundle and the differential of phi minus 1 to the unstable part are contracting. But of course, contracting means contracting relative to some Riemann matrix on M. So it means that there is some Riemann matrix on M, so that this is the d phi over ES and d phi minus 1 over EU are contracting. There are also classical definitions which holds for any matrix, but it's more technical. And also here, I assume that M is compact. So if you are looking at books about Anosov diffeomorphism, they will not usually the definition looks a little bit different because in the non-compact case, this would be not a correct definition. You want the uniform bound of contraction. So in compact manifold, it is always the case. So that's why I don't want to be more precise. And my first corollary is the following. You choose a Nil manifold M, which admits an Anosov diffeomorphism. And as a conclusion, we say that the fundamental group is freely minimally self-similar. So this nilpotent group is automatically freely minimally self-similar. That's my first corollary. So it's a quite strange corollary because basically what you have On one side, you have an hypothesis that you have a certain type of C1 or smooth dynamics on M. This is your Anosov diffeomorphism. So this is smooth or C1 dynamics. And the conclusion is that the fundamental group has a certain type of symbolic dynamics. So this is it connects some, say, smooth dynamics to some symbolic dynamics. And so you can expect here that maybe the proof will involve some topology or some differential geometry arguments, but as I will show you later on, there is nothing like this. At least I think this kind of corollary is very nice for us because this is purely algebra statement. The proof is purely algebraic. You don't need to know anything about differential geometry, anything about topology. It's purely algebraic. Now I would like to speak about a second subject, which are affine Nil manifold. And this subject had a quite interesting history. So first, a Nil manifold is called affine if it is endowed with a flat and torsion-free connection. This is very special. Basically, it's happened it's very unlikely. For example, if you take a Lie group, you know, usually you always have Cartan connection, which is torsion-free. You have another connection due to Sabinin, which is flat, but usually you cannot have both flat and torsion-free. And this is on something very simple like Lie groups. So and Schoenmann, sorry, I forgot the N of Schoenmann. Schoenmann and Milnor made the following conjecture. They ask, is any Nil manifold affine? And this conjecture has been proved many times, and it has been refuted as many times as it has been proved, indeed. So I will not tell you the full story. I will only explain you the end of the story. And for many years, it was almost proved. Means after each refutation means it was almost proved. There was no, and I remember that in the 90s, everyone believed this conjecture should be true. Until 95, so, oops, sorry, I miss something. Ooh, okay. Until 95, where Benoit, maybe you should call it Benoist, but he's French, Benoit, proves the following theorem, that there is a Nil manifold, I will call it MB, of dimension 11, which is not affine. And this was really a big surprise. And his paper is extremely famous. And as a corollary of, I will first say something which is a corollary which has nothing to do with differential geometry. The next corollary involves differential geometry, is that this is very amusing because the fundamental group of MB is exactly an example of not self-similar group. It's easy to find groups, nilpotent groups, which are not transitive self-similar, but finding a group which is not even self-similar is not so easy. And indeed, this is a corollary of Theorem 2, and not the Benoit's theorem, but the proof, but its proof. And I believe that there are smaller nilpotent groups which are not self-similar, but but any computation should be extremely difficult. And the good point is that Benoit's paper, provide all computation we need to prove this corollary. So really, this is a lazy corollary in the sense that it can be proved by using Theorem 2 or Theorem 1, I forgot, Theorem 2, and very lazy computations. And now I came to the following question. You know, Milnor-Schumann conjecture is not correct. So there are Nil manifolds which are not affine. And I would like to find a kind of conjecture which is very related with Milnor conjecture. So now assume the fundamental group is transitive self-similar. Then under this condition, we can ask, is P1 of M affine? And I have to say that this question is certainly not easy, because if you look at Benoit's paper, the first lemma is about the non-existence of certain representations, and the theorem 2 proves that there are representations of the Lie algebra exactly what's of small dimension, so the argument of Benoit theorem cannot be used to show counterexample. So that's not so easy question. First, I was sure that the answer should be negative, but now it's not so clear. At least now Benoit knows this conjecture, and in the last 2 months, he still didn't find a counterexample. So it's a good side. And I have to say that I have a positive result in that direction, which is the following. Assume that the fundamental group is freely self-similar. Not only self-similar, but freely self-similar. Then it is correct that M is affine. And this is an easy corollary of Theorem 2. So you see, there could be some connection between affine structures and self-similarity of the fundamental group. I don't know, but there are some, at least. I have to say that also concerning Milnor conjecture, after Benoit paper, there was a lot of other paper trying to simplify or extend his counterexample, but all of them followed the original proof of Benoit. So really does not, later work does not bring new light on this question. Okay, so now I did explain the statement, and I would like to say something about proofs. And it's quite, and I will explain that the proofs have very little to do with, say, dynamics or differential geometry. So to explain the proof, first I would like to explain what means that the group has a self-similar action on A omega. How to check this. Okay, you choose a letter A and you define gamma prime be the fixator of A. Remember that gamma acts on the alphabet. And then you have a map F from gamma prime to gamma, which sends gamma to gamma A, and this is a group morphism. And gamma prime, of course, has a finite index, and so usually the map is denoted like this. It is denoted like a map from gamma to gamma, but it is a virtual endomorphism. It means it is an endomorphism defined on a finite index subgroup. And let me remember the definition of the F core. It is the biggest subgroup K in gamma prime, which satisfies the following condition. First, K is an invariant subgroup, distinguished subgroup of gamma, and it is invariant by F. So, and it's clear that there is a biggest subgroup in gamma prime which satisfies this. And to simplify, to now assume that the action is transitive, and then the F core is precisely the kernel of this action. This is well known. And indeed, there is a correspondence between the faithful transitive self-similar action and the virtual endomorphism F with a trivial F core. That's a very well-known correspondence. And by mean, it is a correspondence modulo some conjugacy. But basically, you can go from one side to the other side. So it's very, very well known. And now I would like to explain at least the proof of corollary one, okay? Because I will not explain all proofs, but I will explain the two main ideas. And to explain the two main ideas, I will explain two main ideas to prove that if M is anosoph, then pi 1 of M is freely minimally self-similar. So you have an anosoph diffeomorphism from M to M. M is a Nil manifold. So it induces an isomorphism from the frontal group of M to the frontal group of M. Indeed, not exactly because if phi has a fixed point, then it is clear. But usually phi is simply defined up to an inner automorphism. So phi, this 5 star is not really defined. It's up to an inner automorphism. But we don't care about this inner automorphism. And by Malchev theory, it induces an automorphism F from NQ to NQ. What NQ means, NQ is a Q form of NR, which is generated by log of gamma. Remember that the exponential is a diffeomorphism from the Lie algebra to the group. So the log also is a diffeomorphism from the group to the Lie algebra. And when you take the log of this finitely generated group, then it generates Lie algebra, which is a Q form of the Lie algebra. And now I take the Zariski closure, K, of the power of F in the automorphism of NQ. So this is an algebraic group defined over Q, and I take the Zariski closure of. And for simplicity, we'll assume that F is semi-simple because, okay, we'll not explain why, but it can be, we can always assume this. And so it implies that the connected component of K is a torus, algebraic torus defined over Q. And now we have the F, and what we want is to find another element in the torus, J, such that the virtual endomorphism from gamma prime to gamma is suitable, means it provides a minimal self-similar action of gamma. So you see, you start, this F is essentially the anosoph diffeomorphism. You take the Zariski closure of the group generated by this, and you are looking at elements in the Zariski closure which satisfy some suitable condition. And therefore, we need to investigate the rational points in rational tori. And that's the purpose of Theorem 0, of the next theorem. So the next theorem, which is a key step in the proof, is a theorem about rational tori. So I take an algebraic torus defined over Q. Now it's totally new hypothesis. I totally forgot Nil manifold, nilpotent groups, and so on. I choose K as a splitting field of H, means a minimal field, such that when you extend to K, the torus is split. One way and let X be the group of characters of H. And K, the splitting field of K, means that when you take the value of the character on some rational elements, then it is an element of K. So the splitting field of K is a finite, the Galois finite extension of Q. And now I fix an integer n, and Theorem 0, or theorem about tori, that there is some element G in HQ which satisfies the following two conditions. First, when I take the character chi of G for any non-trivial character, it is never an algebraic integer. Of course, it is an algebraic number. It's an element of K, of the number field K, but it should be never an algebraic integer. And B, and now if you take any ideal pi, so this means an ideal in K, not it's a prime in K, not in Q, which divides n, we want that chi of G is congruent to 1 modulo n o pi, and O means the ring of integers of K, and O pi, as usual, is a completion, the pi completion, periodic completion of O. So the theorem 0 tells you that there are some rational elements, which satisfy two types of conditions. I will not explain anything about the proof of Theorem 0, which involves a lot of Galois theory. But I will explain why it is connected with our problem. So Theorem 0 is one of the two ingredients of the proof of Theorem 1 and 2. So Theorem 0 is enough to prove something like, if you have a spatial grading, then gamma is transitive self-similar. This is enough. But we want something more precise. We want that gamma is minimally self-similar. So to go from transitive self-similar to minimal self-similar, we need something more. And also we need freely, but I will not explain. So you choose a virtual endomorphism with a trivial F core. And now I will explain what means the minimality condition means. So you said gamma 0 is gamma, and you define a series of subgroups, gamma n plus 1, all gamma of gamma n, such that f of gamma belongs to gamma n. So by this way, you find a descending series of subgroups. And in addition of that, it's very easy that the indices are decreasing. The index of gamma 1 and gamma 0 is always bigger or equal than the index of gamma 1, gamma 2 and gamma 1, and so on. That's really easy. Remember that the correspondence, let's consider the corresponding action of gamma on A omega, where A is gamma 0 divided by gamma 1. And this action is minimal exactly if the indices are constant. So the decreasing, remember that the indices was a decreasing, non-increasing sequence of integers, and want this sequence to be constant. And so we need a criterion for the stability, for the equality. Okay. And the criterion is a bit difficult to explain, and it requires a lot of definition. First, you start with your group gamma. And if you use a log map, you can realize gamma as a subset of NQ. This gamma means log of gamma. But gamma, of course, is not abelian subgroup. It's not stable by addition. But this gamma is not anything. Indeed, gamma is always a finite union of cosets. Exactly what I mean is the following. I mean that gamma lies in some abelian lattice, additive lattice, lambda, and gamma is a finite union of n lambda coset for some n. Here, I forgot to write for some n. And this is for some additive lattice lambda in NQ. So gamma is not a lattice, but it is as close of an additive lattice as possible. Don't confuse. Lambda is an additive lattice in NQ, and gamma is a co-compact lattice in N, in the group N. So this is multiplicative subgroup. This is an additive subgroup. So now we start with some automorphism of NQ. Let's assume that F is semi-simple, and we define by Q of H the algebra generated by H, and this is a subalgebra of NQ. So of course, elements of NQ of H are no more endomorphism of the Lie algebra, they are just linear maps. But because F is semi-simple, Q of H, of course, is a product of number fields, finite products of number fields. And let's introduce the definition O of H, which is a ring of integers of Q of H. And this definition, O of H is maybe a bit confusing because usually H does not belong to O of H. H belongs to the fraction ring of O of H, but not in O of H itself. So now we assume that gamma lives inside some lattice lambda, that gamma is a finite union of n lambda coset for some n, where lambda is not only an additive lattice, but it's an O of F module. That's a very important condition. Of course, it's always possible to find such a lambda because gamma lies in some lattice, so the lattice lives in some O of F module and so on. And you denote by H the Zariski closure of F to the n, the power of n. And for simplicity, we'll assume that H is connected because you denote by K the splitting field of our torus H, by O the ring of integers, and by H the character group of H. So when you have all this definition, you can give a nice criterion for F to provide a minimal action. But you see, it requires a lot of things. And the criterion is the following. Assume that chi of F equal 1 modulo n o pi for all prime pi dividing n and all character chi in X. Then the corresponding self-similar action of gamma is minimal. It's a very technical criterion, and at first, let's say, the proof is relatively elementary, but the statement is really painful. But you know, we need minimal action, so It's not so easy to find. And the application of this criterion is the following. So we have, remember, we have an automorphism of Nq, which comes from the Anosov structure. And I take the hierarchy closure of the group generated by phi, and up to some details, let's say we assume that phi is semi-simple and that H is a torus. So this basically, to make this, maybe you should take the semi-simple part of phi, and to have the torus property, you should find not phi itself, but some power of phi. That is really not a big deal. And as before, there is a lattice lambda and some integer n, such that lambda is the O phi lattice of Nq, and gamma lies inside lambda, and gamma is a finite union of n lambda coset. So that's always exist. And now theorem 0 implies that there is a f in HQ which satisfies some condition. I will not recall it, but I will explain later on what the conditions are. But we notice that O of f is automatically in O of phi. So the criterion will say that the virtual endomorphism of f from gamma to gamma induce a minimal action. So let me remember exactly what theorem 0 says. Theorem 0 says that, just repeat what I said before, that there is some f in H of Q, such that K of f is not an algebraic integer, for K is not a trivial character, and for any prime pi dividing n, chi of 5 equal 1 modulo n O pi. So what is the effect of condition A and B? A is a condition which implies that the F core is trivial. And condition B implies that F satisfies exactly the criterion for minimality. So this condition A and B were exactly made in order that you have a faithful self-similar action, A, and an action which is minimal, condition B. So you see, this is a way theorem 0 is connected with minimal and faithful self-similar action. I hope now it's clear why there is this technical statement and what is the consequence of it. Right now, my explanation, I only gave explanation for the following, that the existence of an Anosov diffeomorphism on the Nil manifold n over gamma implies that gamma is minimally self-similar. So right now, I did not explain why it could be a free action. But I explained the two main ideas, and the two main ideas are exactly the same for Theorem 1 and Theorem 2 and corollary 1 and 3. So that's. But now I would like to explain a little bit more from why we can get free actions. And the free action here, you need something more to get free actions. And free action comes from the following fact. Assume again that M is a Nil manifold endowed with an Anosov diffeomorphism. Now, the fact that P1 of M, the fundamental group, is freely self-similar requires an additional statement. And the statement is what is called Manning's theorem. And Manning's theorem proves that if 5 is an Anosov diffeomorphism of M, then you remember 5 star now can be viewed as an automorphism of the Lie algebra. So it's a linear automorphism. So So the set of eigenvalue is well defined. Indeed, 5 star is only defined modulo some inner automorphism, but inner automorphisms do not contribute to the spectrum. And Manning's theorem says that the spectrum of 5 star contains no root of 1. And this is exactly what we need to prove freeness. Exactly to prove with this, we can prove that the Lie algebra, complex Lie algebra, has a very special grading. That's condition for the existence of a very special grading. Indeed, this Manning's theorem is not optimal at all. Means later on, after Manning's proof this theorem, later on he proves that indeed 5 star is a hyperbolic linear map. It means no eigenvalue of absolute value 1. But for us, it does not change anything. And at least this very old theorem of Manning's has the advantage to be extremely elementary. The proof that it is hyperbolic, okay, no, there is an element, I know an elementary proof of that, but in the original paper of Manning's, it was really difficult, very difficult theorem. But nowadays, everything is much more easy because we can use rational homotopy theory, which did not exist at that time or was not clear at that time. So nowadays we can say much more without too much difficulty. But at that time, Manning's theorem was a really beautiful theorem. And now I would like to explain what is involved in Theorem 0. Theorem 0 is based on Galois theorem. It means on Chebotarev and Dirichlet theorem. Galois, classical Galois theory. And the proof of the criterion is based on the notion of 8 of an endomorphism. And the notion of 8 endomorphism is very similar to the notion of they 8 of algebraic numbers in number theory, except that here I don't need infinite places. So I don't have time to explain what is this 8 theory for endomorphism and how to prove the criterion. But at least I can say it is based on some idea like that. And I would like to say a few words, very quick words about complexity computations.
Only if it is quick, because we have collegiado at 4 o'clock, so we...
Yeah. It will be 1 minute.
Okay.
So now for complexity computation, I choose a connected and simply connected nilpotent Lie group. And you see that you assume that NC has a spatial grading and that N contains some co-compact lattices. And you see the condition of self-similarity only depends on NC. So it only depends on N. So usually N contains many co-compact lattices, and all of them are self-similar. And so you can ask what is the complexity of these co-compact lattices? And by this, I mean, what is the minimal degree, the cardinality of A, of a faithfull transitive or minimal or free action of gamma on A omega? So basically, how much A depends on gamma. And the minimal degree is the complexity of gamma. But really, I don't know, there is no formula for the complexity of individual group, but there is a nice formula for the complexity of commensurable classes, which means for the minimal complexity of gamma when gamma belongs to some commensurable class. And this is, and this is where the complexity occurs. And this involves some invariant of arithmetic groups, groups over Q. But of course, I don't have time to explain. And this is really a much more algebraic subject than what I speak about before. But I will skip here and I will say nothing more. So thank you very much for your attention. And I hope to see you sometimes directly, so not only by internet. Thank you very much.
Thank you very much for your nice talk. And I open questions. If anybody has question, right? But first, let's speak. Let's thank speaker, all right, for the nice talk, right? Unmute, please, and now, if anybody wants to ask a question, just unmute microphone and ask.
I have a question.
Sure.
Okay, Olivier, nice to see you, and thanks for the great talk. My question. Okay. So the question is the following first. So in Benoit's example, the fundamental group in his case, so the Nil manifold Benoit constructed is of dimension 11, right?
Right.
So the point is that when you look at the fundamental group, what is the nilpotent class of this group?
Oh, yes. In Benoit's example, they are, as it is called, filiform Lie algebras. So the nilpotency class is as big as possible.
I see.
But I forgot how to compute it. Probably it's 10, I would say.
I see. No,
I forgot exactly what the definition of nilpotency class. Commutative groups, are they of nilpotency class 1 or 0?
1. Commutative groups are 1,
okay,
yes.
so it's 10. So the correct answer is 10.
Okay. No, because I remember a few years ago, actually, in private communication, Professor Said, he gave me an example of a group which is not self-similar, but if it is of torsion-free nilpotent group, which is not self-similar, but it is of nilpotency class 6, right? And actually he had a question, a specific question that, do we know any example of a nilpotent group of nilpotency class 3, which is not self-similar?
No.
Right, because I think that, so he has proved with Berlato together that all of nilpotency class 2 are self-similar. But the question was, what's going on with nilpotency class 3? So that's why I thought that maybe you know something in this direction.
No, I don't.
Nilpotency class 3, we don't know.
No, for Nil, I don't know because let's say the trick is the following. If a nilpotent group, if the center has rank 1, then self-similar implies transitive self-similar.
Yes.
And therefore, I can use the theorem. So I can use characterization. But yes, for those who have a center of rank bigger than 1, I don't know anything at all.
Mm-hmm. Yeah. Yeah, usually because one can restrict it to the center and then see what's going on. But when the center is dimension 1, it's a less complex issue than when the center is of higher dimension. Okay, it was just, I wanted to know it because I thought about this long time ago, but wasn't sure if the answer is yes or no, but it appears that we don't know. Thank you.
And also, someone told me that there was someone found a very similar example to Benoit in dimension 10 instead of dimension 11. But let's say I didn't have time to look at, and okay, basically the ideas were strictly similar to Benoit, so it does not.
I see.
It was basically the same.
Mm-hmm. Okay, good.
Any other question?
Yeah.
Please.
Can you hear me?
Yes,
Yes.
I'm sorry, my speech is a little difficult, but let's see if you can understand me. So, in Manon's theorem, we have a statement about the spectrum, and that's very interesting. The spectrum came up in the study of groups which are not just similar, but finite states. And in that case, we have that the spectrum is strictly less than one. So this is one of the exceptional circumstances where finite states is translated into spectrum language. Did you understand what I said?
Okay, Said. I'm really sorry, but the communication is not very good. Means the sound was not very good. It seems to me that you mentioned your works on, say, untransitive self-similar. Is it correct?
No. I'm mentioning a theorem about spectrum and finite states.
Spectrum of finite states. Yes.
Spectrum
finite
of
states.
finite state automorphisms. And if the group is self-similar and finite state, transitive, self-similar, and finite state, its spectrum is strictly less than one.
Yeah.
Yes.
Yeah, no, it's clear.
It's very interesting. It seems to have some kind of connection to Manon's theorem.
Okay, you are speaking about finite states, self-similar actions.
Yeah.
And here, I don't, let's say, I did not investigate that question.
Yeah.
And I'm suspecting that these kind of methods are not good enough for that question. The method I explain in this talk.
I see. Well, this, okay. I'll stop there. This was very nice.
Okay.
There's a lot to learn from your work. Yeah.
Anybody else want to ask a question? Well, if not, then let's thank speaker again.